Give it up for Brad Dixon.
Thank you. So I'm Brad Dixon. I work with Carve Systems. We have a lot of fun working with systems that involve embedded or IoT devices, trying to do security assessments and penetration testing on the whole system. And this is going to be a presentation, a quick one, about an attack technique that we found repeating itself as useful more times than we thought it would. And I'm going to describe this as being useful because it works, it's easy, it's pretty dramatic, and it provides a teachable moment about designing more secure systems. But it is a novelty. And it's a novelty because it's risky, it's crude, and it's perhaps redundant to a lot of other great techniques that are out there. But it sure is fun. And when you do this device, like you can demo this attack to your mom, and she'll just be like, "Oh, I get it." So let's just get to the demo. So to set the stage here, we've used this on a lot of devices, but this one in particular is an embedded Linux device with U-boot as the bootloader. There's no JTAG. That's actually been turned off with microfuses inside the CPU. So that's gone, can't find it. JTagulator was great, but couldn't find JTAG at all. And because this device had some challenges before, let's say, it had a homegrown secure bootloader added. So getting to the demo here, this is the system booting up. And you'll see why we call this pin2pwn in a moment. This is my trusty, 1995 multimeter just jamming into the flash chips. And I'll show you where in just a moment. But as the system is booting, it's doing a cryptographic checksum across the flash image. And when that checksum doesn't match what it's expecting, it does a fallback to a secondary partition. And it's going to start that in just a moment. And as you can see, using a serial console on these devices, you can track what's going on. I didn't put the clip in there, but I'm again poking the flash device to get the second partition to fail as well. And they designed this device to not respond to any serial input. But what happens is they've misconfigured it so that if it fails twice in a row, the primary and the secondary partition, I get a U-boot prompt. Excellent, that gets me in. So the primary misconfiguration was not checking their failure paths. That happens, as I found out, more often than you would think. And there's also going to be two kinds of flash devices you'll see in these demos. This is a parallel flash device. It comes in a standardized package typically, a TSOP48 package. You can actually attack it from the left or the right side. I'm attacking on the right side between two of the data lines that feed data out of the flash device when it's called by the CPU. And as you saw, it's pretty low tech. You just poke it. But there's been a lot of prior work on this. Glitching as a form of attack has been done numerous times and just some really amazing stuff about like extracting cryptographic keys with transient glitches induced by a number of manners. There's also been other blog posts about this precise thing, using a transient electrical fault to get a failure mode that's advantageous to doing a penetration test. And so there's some of the links you can check out. But what I want to do today is just provide more detail so that when you sit down, pull out some devices from the closet, try this, you might be surprised, as I was, how often this works. I have to warn you, well, first of all, this is Grog. Grog's our mascot. Sometimes, you try elegant techniques and they work. Sometimes you just beat stuff with rocks. And you get what you want that way. But you can definitely break your hardware doing this. I haven't yet destroyed anything, but you can. And the way you'll do that is by exceeding, there's an absolute maximum current that can go out of each IC device. And if you exceed that for too long, then that device might just be, kaput. The black smoke comes out. You can also temporarily cause a device to fail. They have sometimes protection circuitry so that if you exceed the operating conditions, that pin just shuts off. Usually power cycling will fix that. And I've had that happen a few times. And of course, depending on what access you have to the device, like if you have JTAG, you don't need to do this. If you have other means to get what you need, use the safer means, certainly. It will prevent you from breaking something. If there are any time travelers in the audience, go back and listen to Joe Grand's and Joe Fitzpatrick's 101 Ways to Brick Your Hardware. I think I'm adding a new manner to do so. So let's get to the details about how can you mount this attack yourself. This is a general architecture diagram for the kinds of devices that we work with. CPU devices, 32 or 64-bit processors, running Linux, using typically a bootloader like U-boot. And you're trying to interrupt the communications between the external flash device and that CPU. These can either be serial or parallel flash devices. The reason that this works is that systems boot in stages. And what's being shown right here is the activity on the flash bus. You don't need to, looking at trying to decrypt the details of this by zooming in is not helpful for this, but you want to get an idea of like the wall clock timing on this and figure out, well, when is the bootloader being loaded, like is shown on the left? When is the kernel being loaded? What's the duration where the device is booting? And then where does the user space init process kick off? And you can actually attack in 2 different places. The most successful for me has been interrupting the loading of the kernel so that you fail to a U-boot prompt. But I'll show you an example in a second of something that was actually much more surprising to me. So in this example, this device had actually been pretty well secured. This was a device where JTAG wasn't going to be an option, based on how they had designed the hardware. But I found a point later during the init process where poking the serial flash device caused the init process to fail and give me exactly what I wanted out of this. A root shell on the device. Yeah. So this kind of misconfiguration is much more rare. Forgetting to have a useful failure mode for U-boot, that's pretty common. I've seen that a lot. But this one was more rare. And the reason for it is this embedded Linux system had been really cleanly set up. It was great work. But they had left something in there to help the developers out, that when the primary application started up, it would grab all the serial ports, throw up an authentication prompt. It wasn't Getty. It was something that was built into their application. But then if their application, for whatever reason, failed, the next step in the init process would be just run a shell. Now, another thing that happened, another characteristic of the system was important to this. This system was using BusyBox. BusyBox is like what's called a multi-call binary. It's like a Swiss Army knife that does all the things that a typical Linux system needs, but does it with just one binary. And so since most of the pages for that had already loaded before the application we caused to fail had started, when that application failed, even though I was screwing up flash for it, BusyBox was already resident memory. I think it might have been different if it had to go load other pages, because I wouldn't have been able to time that attack very elegantly. This is also an example of a serial flash device. These typically have an 8-pin pinout, very standardized, much bigger device, so you can use a multimeter probe to poke at this. And I was poking between the chip select, which says, hey, flash device, read me out some of that data, and the actual data output on that. So here's another example. This was an LT router. On this device, as you can see up in your top left, there's a little dim-looking CPU module. The flash device was on the underside of that dim device, so that's outlined in the red box below. So to get set up for this, I had to pop that device out, flip it over, put my pin where I wanted, throw a little blue tape on it, and then pull that pin out just a fraction, a couple millimeters, so that it'd be ready for the attack. I'm working on the left side of a parallel flash device, another TSOP48 pinout. It's a standardized pinout, so you can find this pretty frequently. And I'm probing the chip select, the command latch and address latch lines, shorting those 2 out. And what those do is when that command latch line is toggled, it says, here's a command to make sure you read this in, do what I'm asking. And then here comes an address. And just by screwing with the logic on that, you got this flash chip confused enough to do what I wanted. So this is a quicker demo. On this device, just a little boop on the pin, and we're going to end up back at our U-boot prompt, which is where we wanted to get on this. So doing your own pin-to-pwn attacks, pretty straightforward. You need to survey the hardware. Pop that thing open. You don't need to take anything apart at the PCB level, but just the key things you want to do is find all the flash storage devices, figure out how you can access them. You need some way to monitor the boot process. A serial console is great because that's probably the access that you're going to get. The developers will turn the serial port on when something goes wrong. But there's other ways that you could do that perhaps. Monitoring with a logic analyzer and just getting a wall clock time on it. You need some data sheets to figure out on the flash storage devices that you have, where can you probe successfully. There's some trial and error on this. Not everywhere I tried worked on each device. So you're going to have to take a few cracks at it. And you need a way to be able to understand when the device fails. Maybe it's LEDs. Maybe it's something on the serial console. There'll be something. Because the last thing a developer wants is for something to go wrong in the lab and for their device to be bricked. They left a door. Find it. After you selected your pins, you're going to start poking at that. This took me a try, usually about 6 or 8 attempts per device, just to get the timing right on it. But it's something you can work through pretty quick. Make sure you power off between each test. If some of that protection circuitry in the IC gets engaged, power cycling, it's going to help you out. And then monitor for a different operational state, one that's not the normal one. Getting U-boot prompts, pretty common, but some devices have different failure modes, like enabling networking ports or failing to like a USB device firmware upgrade. You'll need to find those. And you need a little bit of luck on this too. So we pulled out all the devices in our closet and we said, hey, let's go for this. Let's see what other devices can do this. And about a little bit over 50% of the time, we were able to get some failure mode that was helpful to what we're doing. Getting root on one of these devices is really just the start. That's kind of like day one of our project. It just helps us do the rest of the work. But it's really cool to be able to demo to people to say, watch this, boop, and you end up with what you want. It's a great demo. I highly recommend it. But let's talk about some of the places where I was unable to get root. The devices that have thoughtful consideration of how to fail, those are pretty resistant. The best ones were the ones that would reset if they were unable to read flash on it. From a consumer perspective, that device is bricked. That's probably maybe a bad thing for business. But from a security perspective, that's a proper reaction to it. Ways that you can improve your design or give recommendations to others. If you can all turn on watchdog timers early in the init process at the bootloader level and then start servicing them in user space. So that if something interrupts in between, you're going to confound an attacker to a degree who's trying to get at this device. And just be very cautious about shipping failed to debug mode systems. Those are exploitable. You just got to find the way to get in. The other one is really a design decision. Hide your pins, hide your traces. BGA, or ball grid array devices, they have an IC with little balls underneath. That mounts directly on the PCB, and the PCB designer can actually take signals and route them immediately through a via to an inner layer of the printed circuit board. When you're at an inner layer, it's hard to get at them. Traces that are on the outer layers of the PCB, you can actually scrape off the solder mask and get at those, but you're going to have less options. And so it just makes it harder for an attacker. So BGA devices, some security conscious PCB design and PCB routing can make a big difference. And the last, which I think everybody should be doing when they lay out these devices to help improve security, is just be very terse about what you're doing. If you have a serial console, certainly don't accept input on it unless you really want that for some reason. And boot that thing fast. You can get like embedded Linux systems to boot well under a second. And it just makes it hard for a hand-timed attack like this. You could do something more elegant and crafty, of course. But that's more work an attacker. Maybe they'll move elsewhere. So that's the last bit of this. Max is here somewhere. Max is right there. We're going to be outside to take some questions, and if you ask some good questions, we want to have something for you. But I'm Brad Dixon. Thanks so much for your attention. Appreciate it.